I am delighted to introduce you to our speakers, but before I introduce you to them, I want to give you a sense of the vibe of this. So they're going to build an argument for you. You are going to evaluate that argument and then think of things that you want to say in response to that argument. And so if you have things you're thinking of during their presentation, go ahead and pop those in the chat and we'll use those to begin the discussion period afterwards. But we're going to have room for discussion afterwards. So like think of things that you want to walk away from this with having talked about. Okay. We have Rosemary, Russ, and Ryan Stowe here. Rosemary Russ is background is in physics education, and is now living as an associate professor in a college of education. And then Ryan Stowe is background is in organic synthesis and now lives in the chemistry department at University of Wisconsin. Both of them are at University of Wisconsin. You'll see. I didn't need to say that. Okay, take it away.
All right, we're going to do the screen share thing. It's going to be awesome. All right, thank you very much for the kind intro, Alina, and thank you, Alina, Vicente, and Nikita for organizing this event. I'm really hopeful we have some exciting conversation that follows this presentation. As I said earlier, if we finish this and nobody has anything to talk about, I will just be very sad. So we will be thinking with you today about how we can support students in using chemistry knowledge in everyday life, which is a goal I think that many of us share. Before we get rolling, I want to acknowledge the research group I'm fortunate to be part of, and in particular, much of the data that we're going to be talking through later in the talk was collected and analyzed by Kimberly, Kara, and Nicole. So Kara's over here wearing an awesome blue jacket. Kimberly is right next to Aubrey in blue, wearing kind of a burgundy thing and a brown coat, and then Nicole is right behind my right shoulder. This was at a community band concert where they all came out to say hi and support the band, which was super cool. And thanks also to some funders.
So when Ryan and I have been in various places across the country talking with folks about why do we want people to take chemistry classes at all? What is the value of these courses that we work really hard to design and teach? And there's a couple of answers that are pretty common as we talk to folks. And the first one is chemistry knowledge will help folks to make more informed personal and political choices. That some of these students that are in our classes will go on to be chemists. And so as a result, they need to have the knowledge that we're teaching them in class. That chemistry is just really cool and actually people should be excited about it and become engaged with it. And then finally, that chemistry helps students to build critical thinking and problem solving skills that will be useful in their life. And we get some variation of these questions when we talk about this. Today, we're going to be focused on really the first and the last ones, which have to do with that students should take chemistry classes because chemistry knowledge and practices are useful in daily life. Now, what do we mean by useful in daily life? Noah Wyeth Feinstein has a definition where he describes things that are useful in daily life in that they help people solve personally meaningful problems in their lives, directly affect their material and social circumstances, shape their behavior, and inform their most significant and practical political decisions. And so we would hope that chemistry would be useful in this way. And this is not new. When we look back over the course of chemistry education literature, more than 50 years ago, people were saying these kinds of things, that this information is useful in forming a rational philosophy, and it has urgent implications for how people think about atomic power sources at that time, which were very important, or that they can use the methods of chemistry in the solution of problems of concern to the individual, the community, the nation, and the world. And so we have this hope that chemistry is going to be useful for people in their lives as they go about making decisions outside of our classrooms. The way that we have largely instantiated this desire for things to be useful in folks' daily life is that we've taken a look at what are the things that scientists know or do. And we've said that that is a particular set of things. And since scientists know and do those things, then learners should also know and do those things. And so we have a lot of research that focuses on scientists' understanding of topic X, and then we want to be sure that students understand that in a similar way. And this is how we have largely attempted to instantiate this goal of having chemistry be useful in daily life.
And
So
we would argue, oh.
No, go for it, Ryan.
Oh, okay. We would argue that a great deal of contemporary scholarship in chemistry and science education assumes that if learners can construct things, arguments, models, explanations, et cetera, that look like what working scientists construct, then we will have succeeded at preparing people to use science knowledge in daily life. And I would argue that we're actually pretty good at supporting students in constructing knowledge products that look like what an expert might create. We can slice apart learning environments in various ways and think about how different facets of those learning environments relate to student construction of expert-like knowledge products. So we can take a look at what's going on in the classroom from video data using an observation protocol like the COPUS. We can take a look at the intellectual emphasis of what students and/or instructors are doing. So are they making lists of solubility rules? Are they constructing causal stories? Are they drawing pictures of various things? And we can examine the sorts of performances emphasized and rewarded on exams. And we can do this with protocols like the three-dimensional learning assessment protocol. So are students mainly recalling facts and engaging in representational skills, or are they constructing causal accounts for phenomena, models, arguments, things of that nature? Ideally, these three facets of a learning environment would align so students are receiving a coherent message about the sort of intellectual work that matters. We built what we understood to be an organic chemistry course that embodied best practices across those three different facets of the learning environment. So that is instructional practices, so the pedagogy in the whole class meetings, instructional emphasis, the kind of intellectual work that is emphasized in those meetings, and assessment emphasis. And so all parts of the course place substantial emphasis on constructing causal accounts for how and why things happen. We'll go through each of those aspects of the learning environment very quickly. So when I say 3D tasks here, I'm talking about assessment items that ask students to connect large grain ideas such as energy and bonding interactions to how and why phenomena unfold. And so you can see the vast majority of the points in our first and second semester organic course on both midterm exams as well as the final exam ask students to connect energy and bonding and similar ideas to causes for phenomena. If we take a look at what's going on in class, these two timelines represent acid-base instruction during first and second semester of organic. And we can see that the vast majority of class time involves students or the teacher connecting energy, bonding interactions, and things of that sort to causes for phenomena. If we look at level of interactivity, where in gold we have instruction that isn't lecture, but involves some other teaching method where students are doing something that isn't just listening, we can see that there's quite a lot of overlap between the green and the gold. So when students are interacting in some way in class, that interaction often involves them constructing some sort of causal account for a phenomenon. So we can relate all of these to an outcome using assessments of this sort. So here students are asked to evaluate the claim as to the outcome of a reaction. And so in this prompt, students are told that product B is going to be the major one and asked to evaluate that claim. So we can take a look at what it is that they write, and we can evaluate the extent to which what they write aligns with what an expert might write. So here we have the prompt at the top, and at the bottom we have several codes describing the ideas students connected in the context of this prompt. So here in gray, we have 20% of the class didn't talk about structural features of the transition state or intermediate relevant to the outcome. If we look in kind of light green, what we see is that about 14% of the students who were surveyed talked about charge delocalization or the energy of the intermediate or transition state relevant to this process, but didn't connect them. And kind of a teal, we have 31% of students who connected the spreading out of charge in the transition state to the relative energy of that transition state. This is a very reasonable response that many of us in organic would be pleased with. And then 35% of the class did the more precise thing, which is connect the structure of the transition state to the relative energy of that transition state rather than intermediate, which is the code of 2. The point of this isn't to go into great detail on this coding scheme, but instead to say that the majority of students enrolled in this sort of course, so 66%, constructed an expert-like explanation, which is right here.
So the question for us is, it seems like we've designed a course that does successfully have students engaging in the kinds of thinking that scientists engage in. And so for us, though, this raised the question of what does constructing canon-aligned explanations or not tell us about how learners might use knowledge in daily life? So just because they can do these kinds of tasks and be successful on them, does that mean that we're necessarily achieving those goals that we talked about at the start of the presentation about using science in their daily lives, or using chemistry in particular in their daily lives? And for us, when we go back to this argument of, does having students do the thing that scientists do the things that scientists do, or learn the thing that scientists do, does that actually support people to be successful in their daily lives? And what we're going to argue in this presentation is actually, we don't think so. That in fact, this model that we've all had for how we construct our courses, how we design instruction, that all of those things actually don't support students ultimately in the goals that we have for them.
So if we're thinking about constructing knowledge in daily life, it might be useful to consider what it actually looks like to use chemistry knowledge in life. And I'm going to call on an example that's very close to my own lived experience, and maybe many of yours as well. Relatively recently, I think in the last couple of months, there were a whole bunch of stories coming out in the New York Times, Washington Post, and other outlets about the possible harms of gas stoves, especially in enclosed and unvented kitchens. You can actually see, looking at the screenshot, that this is one of 4 articles that are all related. People are worried about these gas stoves being banned. I believe a tweet was written that says, "You can take my gas stove from my cold, dead hands," which seems to have escalated quickly. There also are concerns about the impact to climate change of continuously leaking methane into the atmosphere, and that happens if you have a gas stove, and of course alternatives are also a topic of discussion. There's a couple of quotes from this article that I want to draw our attention to. One, that as you are burning natural gas with a stove, a variety of nitrogen oxides are emitted, and once these reach a certain threshold, they can become problematic to folks, especially folks who have asthma or other respiratory conditions. Troublingly, this threshold can be reached pretty darn quickly, especially if you have an unvented stove in a small kitchen. And so if you follow one of the links enclosed in this article, you can see that the claim that was just on the screen is borne out by this evidence. So if we look over to the left, when we're thinking about an enclosed kitchen, after just an hour of cooking with gas, you far exceed the EPA threshold of 100 parts per billion for nitrogen dioxide. This becomes less of an issue as you get to more open concept kitchens, and it becomes less of an issue if you vent your stove. But things like the continuous leakage of methane, even when stoves are off, are still concerns. This was especially interesting to me because until quite recently, this was my stove. And so this indeed is an unvented gas stove. And because I always get asked this every time I talk about it, I now have a different stove, and it is now an induction stove. And I'm happy to talk with you about it if you're very interested in stoves, but that is not the main point of this talk. So how did I go about this whole process?
Yes, so Ryan was put into a very real position of potentially using science in his daily life, exactly the thing that we claim we want our chemistry courses to be useful for. So as Ryan was reading these articles, he was thinking about, should I be worried about my stove? And it turns out Ryan has a lot of knowledge about this topic that could potentially be useful. He knows some chemical equations and formulas like PV equals nRT and other things that I, as a physicist, do not recognize. He also has some more generic knowledge about NO2 having pi bond structure or molecules interacting together. Then he has knowledge that he just knows from his daily life that if stuff has nowhere to go, it's going to build up in one area. So he has really quite a range of knowledge that could be useful for thinking about this. In addition to this kind of knowledge, he also knows some other things that could be useful. He knows that when he's thinking about his stove, he needs to develop a causal story for how this works. He knows that if he doesn't know the answer, he can try to construct one by pulling together different pieces of information. He knows his answer should make sense to him because ultimately he's going to have to make a decision, and did have to make a decision about his stove. He knows he's got everyday experiences that can help him, and that all of his ideas about this topic should fit together coherently as he comes to make a decision about what to do with the stove.
And so thinking in concrete terms about what happened throughout this process, I was motivated to construct knowledge because I don't really want to poison people. And also, I don't really want to make climate change much worse by my stove choice. And so I decided one morning when that New York Times article popped up on my phone to engage with this knowledge construction process. Knowledge was constructed by accumulating information from a bunch of sources. Some of those were popular press like the Times and Post, some were peer-reviewed articles. Knowledge was more justified if it aligned with several sources and or peer-reviewed data. And my partner and I were constructing arguments about possible options and what, if anything, to do in response to the information we were accumulating from these various sources. What didn't happen is I didn't consult an answer key because there isn't one. There's a variety of plausible paths that were available to us, and there are certain things we chose to prioritize or de-emphasize depending on our needs and values. I and my partner decided how and why to construct knowledge. No one told me I had to do this. I didn't only have 50 minutes to do this. I could, in fact, talk to people and use the internet. We also got to decide when we were finished, when we had crafted persuasive enough arguments that we had a path forward, and then we took that path. Chemistry was useful in coming to grips with the problem space, thinking about gas particles being produced by the stove and building up in sufficient concentration that they might be problematic to us. But knowing more chemistry facts wouldn't have solved this problem. If I thought in more detail about nitrogen-oxygen pi bonding interactions, that's not going to help me decide whether I needed a new stove or what stove to get or all the various logistical complexities that go with those sorts of decisions. So there's a lot of other knowledge needed that is not chemistry.
Wow, I'm doing the mute thing. Fantastic. So if we go back to that sort of complicated diagram we had of all the different things Ryan knows and he could use in this context, we see really two different kinds of knowledge. And I separated them on the slide. The top half is what we would typically think of as conceptual or content knowledge, which is just knowledge about chemistry. And this is the standard focus and has been the standard focus of chemistry education research. In the bottom half of the diagram, however, we have what we can think of as more meta knowledge about explanation construction. And this is some tacit knowledge that Ryan and many of us have about appropriate ways to construct knowledge and appropriate types of knowledge to use. It's this knowledge on the bottom that we think of as personal epistemological knowledge. It's kind of a mouthful. Personal epistemological knowledge is referred to in the literature, and that we think about when we think about what are the kinds of things we want students building up in our courses. So to give a little bit more meat to that, epistemologies are defined as people's systems of beliefs, and those beliefs might be either tacit or explicit, about the nature of knowledge and the process of knowing. And epistemologies include a wide range of knowledge, including ideas about what are the aims for my knowledge construction? How should I go about doing that? What are the reliable processes for achieving those aims? How knowledge is justified? It's really quite a range of different types of knowledge about knowing that we all possess and use in different contexts. So what is exactly that epistemologies do? If we go back again to this diagram, we see that there's actually really 4 different kinds of knowledge or conceptual knowledge that Ryan has. He has some procedural knowledge that he can plug into formulas and make things happen there. He has some formal fact-like knowledge that he's learned in school. He has some everyday experiential knowledge that he has just from hanging out in the world doing things. And then he also has some general schematic knowledge, some of which that can sometimes be applied to science or can be applied to other aspects of his life. So those are the kinds of conceptual knowledge he has. What epistemologies do is help you pick out, tacitly again, what kinds of knowledge to use in constructing an explanation. So if Ryan believed that his answer to the question about the stove needed to sound sciencey, then that epistemological knowledge would cue for him to use mostly procedural and formal fact-like school knowledge that he was taught in classes. In contrast, if Ryan believes that his explanation needs to make sense to him as someone who exists out in the world, then he is more likely to draw on this everyday experiential knowledge or generic schematic knowledge. Now, just to be clear, this is clearly a caricature of the model for how epistemologies work. They don't pick out knowledge as cleanly as we've described here, nor does conceptual knowledge fall neatly into these categories, but it gives you a sense of the kind of thing that epistemology can do. It helps you select what knowledge is useful in a given context. There are a range of models for epistemological beliefs about knowledge and knowing that exist in the literature, and we're going to contrast 2 models here just so that we can help highlight the model that we adopt. The first model is a beliefs model. And in this model, people's views about knowledge are pretty stable over time. So what I think right now about how knowledge is constructed is going to be pretty similar to how I think tomorrow. Additionally, I can explicitly articulate my beliefs about knowledge. I can tell you what I think is happening right now and what kinds of knowledge should be used. The other feature of the beliefs model is it's a lot like Piagetian stage models in the sense that we proceed hierarchically through, or we proceed through a set of phases that move hierarchically, so that as you move to ever more sophisticated epistemologies. And then finally, beliefs models also have multiple dimensions of epistemology. In contrast, in our work, we adopt what we call a network model, in which epistemologies are dynamic over a time scale of minutes. So what I think right now about what constitutes knowledge might be different than what I say an hour from now. An example would be right now, Ryan and I are quote unquote possessing the knowledge that's being used in this context. An hour from now, it might be my child as she tells me what I should be wearing to school tomorrow. So I can move fluidly between different models of epistemology. Epistemologies are tacit and inferable from behavior rather than being explicitly stated, and they have varying utility in different times and places. And then finally, in the same way that the beliefs model is multidimensional, the network model is also multidimensional. This apparently is still my slide, so I'm excited to do it. So returning back to our thinking about chemistry and what is the purpose of chemistry. If we think the purpose of chemistry is actually to help people construct knowledge in their daily lives, then perhaps chemistry classes need to be places in which students can explore a variety of different epistemologies, where they can explore and discuss all of these different ways of constructing knowledge. Sometimes that sounds sciencey, sometimes that connect to my everyday experience, and that they would think about how to use different kinds of knowledge in different contexts. And we are proposing that that's actually potentially a better way to help them connect chemistry to what they might encounter in their post-school life. And so Ryan is now going to share a project that he has spearheaded to look at how and why chemistry students experience their epistemologies in the course that he talked about initially.
So recall, this course that we're going to be exploring embodies a certain vision of best practices. So there is a tremendous emphasis on constructing causal stories using large grain ideas like energy and bonding. Success is judged by the extent to which those explanations align with what an expert might construct. So the course in question is an organic chemistry course, the first semester of a 2-semester sequence, and data was collected last semester, which somehow feels like a lifetime ago. This class is structured by 3 50-minute whole class meetings, and there is also one 50-minute discussion where about 30 students work in groups supervised by a teaching assistant. Grades are largely determined by 3 midterms and a final exam, as well as 3 quizzes. And as I just noted a moment ago, assessment and instructional emphasis align with a best practices sense that emphasizes using large grain ideas to make sense of phenomena. We're going to focus our discussion on 2 students, although there is a 3rd student who will briefly appear because the quote was too good to not share with all of you this evening. First up, we have Lexi, and Lexi is a neurobiology major and a pre-med who very explicitly said from early in her first interview that she's taking this class because she has to, and she would like to succeed so she can go on and do what she wants professionally. And Sarah is a student who is a chemistry major and wants to attend grad school. We're going to focus on an interview that happened after students had some experience with the course. So they'd taken 2 midterm exams, they'd taken at least 1 quiz, and I can't remember where quiz 2 falls here, but they'd had some experience with submitting knowledge products on assessments, getting feedback back from that process. And so what we attempted to do with these interviews is to pick out parts of the course that we thought might be sending consequential messages to students about knowledge and knowing, and have students grapple with these messages in the context of our interview. So here you can see a post on a course forum. And this post is basically saying everyday language is really not appropriate for this course. So we don't want to talk about attack, it's anthropomorphizing. I'm very proud of myself for saying that properly. That's a hard word to say. And in a weirdly violent manner. And so instead use these sciencey things. Your explanation should sound sciencey. You have to talk about sigma bonds and aromaticity and sigma star orbitals and all that stuff. And so the question in the context, or one of the questions in the context of this course message was, does it surprise you that the instructor cares about what words you use to describe what's happening? Let's first look at Lexi. So Lexi has experienced the message from exams and feedback to her exam responses in the past that it really matters that you use the words that are authorized on your assessments that are judged by the instructor team. And in fact, if you just work through a lot of practice exams, then you can memorize the right words and where to put them. And really quite troublingly from our perspective, it's not that important that you understand your ideas. It's important that you give the instructors the right words so that they give you credit for your ideas. This signifies to us that certainly on assessments, Lexi framed her interaction as telling the instructor what they want to hear, not making sense of her own ideas in a way that enabled future knowledge construction. If we look at Sarah's response to the same sort of post, Sarah seems to see some utility in using specialized words because they allow us to more precisely describe phenomena in her view. Although, as we'll see in just a bit, Sarah also experienced the message that you have to use particular words in particular ways, or you'll be doing something problematic. One of the other things that we did was we took a look at a practice prompt that all the students had access to, and members of the group came up with sample student responses to this prompt and asked, among other things, does this response signify to you that the student who wrote it understands what the instructor was trying to assess? So there's two parts to this response I want to draw your attention to. One, when we're thinking about stabilizing interactions between solvent and carbocation, a somewhat colloquial set of words was used, this sort of opposites attract kind of heuristic that people might be familiar with from playing with magnets or physics or sticky tape experiments, which I know are chestnuts in many high school chemistry and physics classes. So that's a bit colloquial. And then if we go down to the second half of this answer, it is all of the buzzwords: hyperconjugation, pi conjugation, induction, Hammond's postulate, look at all the things. Lexi was not confident that saying opposites attract was a reasonable thing to do here because you didn't use the right words. You're really supposed to talk about donor-acceptor interactions using the word donor, electron donor in particular, in this case. This was templated in answer keys to other problem sets. Also, it's the way the instructors talk about this. So again, the words are really important, and they're important because your words will get recognized as reasonable or not by the authority figure, not because they let you make sense of something that you've experienced and care about. Here also, you see Sarah referencing this electron donor type language. It's more about the electron pairs donating than the partial negative charge. So it isn't important necessarily, or as important on an exam, that you do something that's reasonable to you. Ultimately, you're rendering this to an authority who will say good or bad, and that's the point of this sort of exercise. There's a couple other quotes related to using right words that appeared across interviews that I want to share to illustrate that this was a pretty pervasive theme that we observed. This is Sarah, who is constructing a response now to that prompt that I showed you a little bit of a moment ago. So Sarah did a think aloud interview, as did all of the interviewees. In the context of this prompt before evaluating student responses, got to use the keywords, got to say electron donor. This is the student that you haven't heard from yet. So Ella is a pre-pharmacy student and had this quote was, as I said, just too good not to share. If you're explaining things to other people, which is actually, oh, I guess it is in this quote, or you're just trying to make sense of something yourself, it's okay to use everyday talk. But if you're making a real scientific explanation, you darn well better not use everyday language. You got to make sure you use the right words, or it's not going to be a real scientific explanation. Now, we're wondering, to what extent did I have to craft a real scientific explanation using the appropriate words to pick a stove, or to decide who to vote for, or what issues to care about, or how alarmed to be about methane leaking into the atmosphere from said stove? So we don't have an exhaustive presentation of the interview data, although of course we'd be happy to talk about it. But I did want to highlight some themes here as we approach closing our presentation part of this. Assessments were powerful sources of how and why to construct knowledge that students resonated with across all of the folks that we interviewed. There was recognition that knowing why mattered to instructors, and some students thought it would also matter to them. But to have a valid causal account, it had to have particular structural elements that the instructors saw as important. It wasn't as important that the students had an explanation that made sense to them and helped them make sense of their own ideas. Practicing similar problems is a good way to get at right answers. Lexi also found it really useful to know what buzzwords to put in what order in the responses to get the points. We also had folks consider where they were getting the knowledge they found useful for constructing explanations, models, and so forth on assessments and in other parts of the course, and that place was not everyday life. Chemistry knowledge is walled off from everyday life knowledge in students' experience with this organic chemistry course. And knowledge was justified primarily by aligning with the key, which is a reasonable thing given the environment, but perhaps not the most useful thing in everyday life. So we claim that many of these epistemologies that students were experiencing from our course and then took up are actually not terribly useful once you leave the classroom, as there is no answer key to life, for example. So if we reflect again on our goal that students be able to flexibly use chemistry knowledge as needed to pursue a range of knowledge construction goals as they navigate their existence in the physical world, we would argue that we're really not achieving this goal with the vision of best practices embodied by our organic course. Now, there are plenty of good things about this course. Students certainly see knowledge as interconnected. They see the power of ideas related to energy and bonding interactions to construct certain sorts of knowledge products. But much of the work they're doing is very different from work they're likely to do once they leave the classroom, we claim. So can we shift this needle? This is hard. This is going to be really challenging work if we take seriously the aspiration that our chemistry classes can prepare folks for daily life outside the classroom. So it seems to us from our interview study that deciding success on the basis of performance on timed resource-limited exams really narrows the scope of the epistemologies students feel they're allowed to draw on in the classroom setting. Students have virtually no agency over how and why to construct knowledge. So recall in the Stowe example, I got to decide to embark on this journey. I got to decide when I was done. There was some communal negotiation of a persuasive argument for paths forward. Students have very little of that sort of agency in our large enrollment organic course, and it's challenging to think about how they could, given the size and scope of the course. But we would argue not impossible to think. We also are constrained by a view that seems very common and pervasive across really K through 16 STEM, that there's a certain body of content that just must be there. And so in organic chemistry, there is a functional group march where we talk about a functional group and how you make it and how it reacts. Then you kind of go to another one and how you make it and how it reacts. And you do that for like 28 chapters. And that's the structure of the course. And if that is the structure of the course, and none of our students, or very few of our students, are going to be making molecules using those sorts of reactions in the future, we are creating a system that is kind of destined to look very little like everyday life. So we probably have to interrogate the extent to which the canon actually has to be what it is if we want to move this needle. But we don't want to end on a hopeless note. We want to end on a hopeful note and really engage in what we hope will be a generative and fun conversation with all of you. And so we want to ask, what would it look like to create chemistry courses around complex and interesting and important phenomena that actually matter to learners? We would argue these phenomena are everywhere. When I was on a plane to Tucson a few weeks ago, I sat next to a guy who runs a company that makes speaker cones, which is a thing that is made in Wisconsin, I now know. And this person was very concerned because one of the only coatings he knows of for speaker cones that make them impermeable to soapy water are fluoropolymers. And he cares about this impermeability because car manufacturers demand it. And so he was upset that there were these states banning fluoropolymers because he was saying that it's a big class of things and some are okay and some are bad. And this ruling by states like Maine lacks nuance. I know very little about fluoropolymers, but in this moment I was thinking, wow, what a really important and relevant and complex context for us to be grappling with in our chemistry courses. Wouldn't it be cool if we built courses around exploring this sort of thing and the various biases that different parties have who might be funding or conducting studies? This guy does sell speaker cones. I'm not sure I totally believed his claim about some fluoropolymers being innocuous, but this is something we could look at. What sort of assessment strategies would actually enable students to have some agency over how and why they construct knowledge in ways similar to what I could do with the stove and what all of us do when we use science knowledge to navigate our lived experience? And then how do we support instructors? I mean, instructors are often very thoughtful, have a lot of expertise in thinking about the plausibility of claims about very, very messy phenomena, certainly from their research lives. But this is challenging work to respond to the substance of students' ideas in a way that allows them to progress forward in ways that are meaningful to those students. How do we create instructor learning communities and curricular supports that instructors can use to open space for student agency? I think we don't know the answers to this, but we'd be interested to talk with you about it. I think that's the end of the talk part of this.
All right.
I
Thank
can
you all
stop
so
sharing.
much. Yeah, that helps. So then if you have any questions, there's so many ways to ask questions. You can raise your hand. You can just open your video and unmute yourself. I don't think you can open your video, but unmute yourself. Or you can post in the chat and I can get those questions going.
I can easily answer the first one. I was typing it and then I realized I can talk. So lab and lecture are decoupled in this course. So lab is a separate course that can be co-enrolled in if you're enrolled in the second semester of organic, but it can also be enrolled in after. And so epistemology signaled as useful in lab is an area we haven't looked into. It would be interesting to explore.
So I would like us to go address Nadia's comment because this is really interesting. And then we'll go to Nicole.
We run into this sort of question a lot. Oh, well, Nadia, do you want to elaborate? Happy to.
Yeah, so I'm probably unusual because I'm the high school teacher here.
Welcome.
But I thought it was interesting because this is what I would love to do. And this is the whole push, K through 12, is that we're using the next generation science standards, which is to have the students behave like scientists, but it centers around the students investigating phenomena and the students driving the learning process. So they ask the questions and you hope they ask good questions that allow you to take them on the journey. But if they don't, you can sort of nudge them along and then they sort of build the knowledge themselves. And a lot of my colleagues, because I've been told that chemists are the most reluctant to change the way they teach.
I don't know, maybe.
Half of my colleagues are into this potential shift and half are very much stuck in the fact that, you know, they have to be able to do the math, they have to be able to give us back what we expect them to say, and it has to be a right answer. And I'm like, but life is messy, it's not like this. And they're not, 99% of my students are not going to become chemists. So what am I preparing them for in my class? So, yeah.
Well, I can comment on a couple things, but I'm sure Rosemary has also some great insights to add. I think there are a number of folks in this call that are trying to change the status quo in college chemistry, and there are more that are not on this call. I think it's been increasingly recognized that having a whole bunch of decontextualized skills that you can plug and chug and you know, recalling a whole bunch of facts is really not going to prepare people for much of anything. And it can be problematic in terms of folks who are already predisposed to success, for example, on the basis of their access to pre-college math prep and other privileges. So there are a few curricular models that try to shift that needle a bit more towards explaining phenomena, and these are chemical thinking from Vicente's group, the CLUE curriculum, Chemistry, Life, Universe, and Everything. There's some organic work as well. However, I want to note that our organic course that I was talking about is got a lot of similarities with transformed chemistry curricula that are currently being enacted across the country. And still, the goal students experience is telling instructors what they want to hear. So I think it would take an even more radical transformation than what we've done thus far to shift the needle towards students being able to construct things they found meaningful in our classes, explanations, models, arguments, whatever. Because for organic, for example, in our course, you're only allowed to construct knowledge insofar as it aligns with the answer key. And so you don't really have a lot of freedom to maneuver and to deal with this mess that we all know exists in the physical world. Did you want to add
Rosemary, do
anything?
you have something to add?
Oh, well, one thing that I think I would add is the optimistic side of me says that if we had secondary high school curricula that encouraged people to use knowledge in different ways, right? To be pretty flexible with knowledge, then you would hope that then they would get to college and that they could say, oh, I understand this class is a time when I do X. And we have some, so that is to say, we don't necessarily want them to have a particular way of constructing knowledge. We want them to be well-versed in a variety of ways of producing knowledge. And so in some ways, the students that Ryan shared snippets with you actually demonstrate some of that sophistication, right? They're able to say, I can understand it, and my understanding is actually separate from this way of constructing knowledge that involves using these special words. So in that way, there's actually some sophistication in what we see the students doing that I think high school curricula of the sort you're talking about could be useful, even if what we're having them do in college doesn't look the same as what we're having them do in high school.
All right, Nicole, take it away.
Hi, thanks for the talk, Ryan. I had a question, and now the discussion makes me have a different question, and I wonder if I can knit them into once, and I'm afraid maybe I'm just going to ask you a messy multi-part question, but I'll do my best.
Awesome.
I joined a little bit late, so I'm sorry if you addressed part of this. When you were talking, it felt very tempting to me to think about Lexi's motivations for taking the course as a prereq might influence her thinking of it as a hoop that she has to jump through, and that might influence some of the ways that she's adopting that sort of like tell them what you want to hear approach. And then I was sort of reminded of that too in some of your suggestions for like the new paradigm of approaches. A lot of them seem to in some way maybe work to change how students view the utility of the course. And then, perhaps thereby student motivations. And I imagine that's something you've thought a lot about. So I was interested if you could talk a little bit more about that. And then the piece I want to add to it is relevant to what you were just saying. It seems like sometimes no matter what we change, we're operating within the system where there is a huge external factor of students' concern about their grades, particularly in organic chemistry. So what are your thoughts?
Thank you, Nicole. I absolutely think that Lexi's perception from the very beginning, I mean, this was the first interview we conducted, which I didn't share any of, was before any experience with assessments in the course. And Lexi was saying, I just need to get through this. So of course that shaped how Lexi experienced the point of the course, how to construct knowledge in the course, et cetera. However, when I think about pre-med prereqs, I end up in kind of an existential crisis. We know these things are acting to prevent people from pursuing careers in healthcare, like they are doing that. And so on what basis are they doing that? It becomes the next question, at least in my mind. If Lexi and people like Lexi, of which there are multitudes in our organic course anyway, and I think in many of your courses, if their experience is just telling the teacher what they want to hear in ways that don't make sense to them, the student, in ways that they don't see as in any way related to like medical practice, that becomes really quite problematic, I think. And also, I'm going to add an addendum here. They could be right. Right? They could be right that the ways that we emphasize knowledge construction in our organic and gen chem course actually look very little like how or whether doctors reason with molecules. I don't think we know the answer to that. And so like, how do you deal with this tangle? I mean, how do you think about constructing a course that in principle looks a little bit more like the professional life of future doctors if you're using this as a gateway or gatekeeper to that profession? I guess I don't know. I think we need to look at how and why doctors construct knowledge. I think if the only person who decides what right or valid knowledge is a person who wrote a key, and you have no say over that, and there's no communal negotiation of more or less justified knowledge, then you're going to be predisposed towards hoop jumping in a way that maybe isn't helpful. So I think exams are part of the problem here, and I think that if just changing the structure of exams isn't sufficient to, in meaningful ways, communicate to Lexi that she has agency over how and why she constructs knowledge. Me from 3 years ago would be appalled that I was saying this, because me from 3 years ago said, oh, make all sorts of prompts that have structure of various three-dimensional knowledge products like claim evidence and reasoning. But I no longer think that's sufficient to move the needle.
Vicente, can we hear from you?
Yeah, thank you for the talk, both of you. As I was listening, I was thinking whether I think I'm in the pessimistic side, not in the optimistic side. So the question for me is, to what extent can we accomplish what you would like us to accomplish with a system and that are not aligned with that philosophy? So I don't think this is a chemistry issue. I think that if you look at physics courses or bio courses at the university level, you will encounter the same. Because all of them are based on the idea, they are reference centered. No, so they are based on the idea that students come to these courses to learn the basic as a fundamental concepts associated with what traditional we call physics or biology. So they are not designed for the students to engage in a more problem-centered approach. That is, okay, what is important is to learn problems, to learn to develop epistemologies that are going to be useful to deal with. No, the ultimate goal is the students will learn the canon of the discipline to a certain level without, in my perspective, the knowledge that most professionals need in each of our subdisciplines is pretty shallow. No, I don't think that you need very sophisticated levels of knowledge in chemistry, physics, or biology to start thinking about complex problems, start looking for information to make sense of those problems, and start kind of providing and evaluating solutions for those. So to some extent, I would like to ask, are we just talking? Because without major changes in the way we are conceptualizing these courses, I don't think that there is a solution.
Yeah, so one, yeah, I share your pessimism and concern about this because yes, it feels like the system is gigantic. At the same time, one of the questions, and I guess I'm just going to respond with another question that we have, which is which parts of the course system contribute most to this constrained set of epistemologies that we see? And so that's, I think, one thing that we do need to do more research on to figure out which parts of the system should we try to be working on, right? If virtually everything is coming from ratemyprofessor.com, then that's a structure that we would need to address. If everything is coming from how TAs are grading exams, then that's just a different kind of intervention. So I think that's my answer to that, is that until we have a better sense of which parts of the system are contributing to the epistemologies we see, we're not going to be able to tackle it because exactly these structures are just beyond our control.
Yeah, and I think you were also suggesting, Vicente, that even with that understanding, perhaps our ability to shift the needle will be pretty limited. And that may be. I think we have to try in our spheres of influence, especially because, for folks like Lexi, we are potentially shutting down future professional avenues for them on the basis of their engagement with our courses. And so to the extent our courses look nothing like what they want to do when they leave, that sort of seems terrible. And can we make that better, even if it's not all that close to what we might dream of in an ideal world? I'm going to try to put a little bit of an optimistic spin, even though I share many of your concerns and pessimism. See, Melanie has her hand up.
Melanie, I think it's time.
It's time.
Okay, can you hear me okay?
Yep.
Yeah, great.
Okay. So I think a lot of people have already said some of the things that I want to say, but I think in some ways you're setting up a straw horse here. You're using organic chemistry as a course and then saying we should be teaching them to make decisions about their everyday lives. And it's not entirely clear to me that organic chemistry is the most appropriate venue for that. There is a tremendous amount of back understanding and theory that you would need to you need to have. I know we've talked about this a lot before. You know, this idea that we can take you know, disarticulated problems and then have students just go through them on problem-based learning. But you know, there's a lot of kind of learning progression ideas, sequences of ideas that students have to be able to grasp to understand what's going on. And I think in chemistry we have this particular problem that's, say, much worse than physics, because everything that students have to understand they can't see or feel or touch. The things they see and feel and touch have to be explained by things that they can't see or feel or touch. And so there's all this background that students have to understand. And I want to align with you in that I agree with almost everything you said, not everything, but almost everything. But I feel like we don't know how to do this, and it's not clear to me that students would want to do it. You know, haven't you had the experience of and here's a fantastic, really interesting thing. Will it be on the exam? And I know what you're saying is we have to get away from exams, but how are we going to do that when we've got 400 students in our classes? So I'll let you speak now. That's not really a question.
Well, I mean, the norms of knowledge construction in school are powerful, right? And this, will it be on the exam, is one of those. I think this, you know, organic is not the first time they've seen an exam that is evaluated by an external authority for alignment with canon. I mean, they've been doing it now for 12, 13 years. And so shifting that.
But I think I think we're asking people to do something that we can't. And I think I do agree with the center here, but we can't do at the college level with 400 students. If I know we talked about this, if I had 30 students and I saw them every day and I could work through case studies with them about PFAS, and they would have a fabulous, it would be great. But I don't actually understand how to go about what you're talking about. And we've done many of the things that you said. We've, you know, done away with high stakes tests for the most part, but it still matters. How do you do it?
Well, we don't know, but I mean, there's a big distance between the sort of status quo most places in organic and, you know, the world's most amazing 30-person class. So there's a lot of room for improvement, right? And I know you agree with that. Yeah, I mean, to what extent have? Oh, sorry. Go ahead.
Oh, I was just going to say, but the reality is the 400-seater class, right?
Yes, but I think the reality is a 400-seater class with a sense that you must cover this large swath of material in a functional group march.
Well, you don't have to do that.
Well, right, but I think most people feel that they do. And so shifting away from that to situations where there are more degrees of freedom from the student's perspective in what counts as reasonable knowledge and how you might construct that would probably be a productive shift. What that could or should look like in a big class, we don't know. I think that the message at the end was that if we care about useful in daily life as a goal space, and a lot of people have said that they do, then we are not currently in many organic courses preparing people with a range of hows and whys regarding knowledge construction. We're preparing them to over-rely on a pretty narrow set of epistemologies. And so I suppose we could say that we don't actually care about useful in daily life. We care about other sorts of things. But I think most folks, well, at least me, early on in organic, I make all these claims about how this is just like diagnosis and it will help you out when you're a doctor. And I don't know if I believe much of that anymore.
Well, we know that that's not true.
Well, yeah. But Rosemary, did you have thoughts to share on?
I think my question, or sorry, my follow-up was just going to be this notion that if we don't think we can do this and we think actually what we're doing is the best that we can do, then does that suggest that we need to state our goals in a different way, or at least to reconsider what our goals actually are?
Yeah, I didn't mean to imply that we're doing the best that we can do, but I also feel as that I feel that we have to be pragmatic about whatever solutions we come up with. This is a huge system that we're dealing with, and it would please me greatly to see us change the system, but right now I don't see how that can happen. So we have to work within it.
Yep.
You got to give me something more optimistic to end this on. We can't.
Well, I think I think we can do better, right? I mean, as Rosemary was noting, we see quite a lot of epistemological sophistication in our students from these interviews. They have considered different ways to construct knowledge, different ways knowledge is justified. Of course, they have all sorts of resources from wandering around the world that they maybe don't feel like they can bring into the classroom. And so I am optimistic that it is possible to open space for them not to have a giant wall between chemistry knowledge and life knowledge, and for them to not see the only goal of class as using hyperconjugation in a sentence, or having cyclohexane do backflips for some reason. So I guess I think we can do quite a bit better, and I think there's a lot of research yet to do to understand what that would look like, what success would even. Like, how would we even know we were being successful at this? Because it wouldn't be as simple as more of them have drawn the right chair conformation or more of them have constructed an expert-like explanation. We would really have to look at this kind of spectrum of how and why they're constructing knowledge and have evidence that they were considering a variety of options and purposefully selected one that fit their goals. And maybe they even had part in negotiating those goals. That'd be wonderful. Did that help, Elena?
Yeah, that should do it. Rosemary, do you have any final thoughts?
No, I really have appreciated, as someone who came from physics, I've appreciated hearing what are the kinds of things that you all are wrestling with, and how are you making sense of it based on the systems in which we all are working. And I'm thinking about the fact that physics and chemistry to many students are so similar, and we think of them as so different. And so I wish that our communities were more connected.
There is a note from Liz in the chat, and then Vicente has his hand up. Yep. I was just noticing the chat exists.
Yeah. Vicente, what do you got?
No, I just want to clarify that my pessimism is not directed to inaction. My pessimism is directed to the fact that I don't think that we are doing enough in terms of challenging the system. So that I think that we are believing that we are confined to think about our chemistry courses in one way, and until we challenge the way we think about these courses, and I'm not talking about only chemistry, about all the science foundational courses, challenge how we believe those courses should work and be, we will be confined to do what we are doing. So if we want to do something more productive, I think that we need to destroy certain things to build new things.
Yes.
I like ending on that. It's like a charge.
Yes, do you want, I can answer Liz's question real quick, but.
Yeah, please. She's also going to be texting you. So.
Oh, well, that's fine too. So Liz's question, if folks are not looking at the chat, is if we think of classrooms as communities of practice, which they are not often, in which learners are legitimate participants in the activity moving from the periphery to the center, is a student-driven epistemology the goal? Is the analysis here on an individual rather than a system level? Which is a great question. But so in this sort of course, we don't have too many options to see sort of student groups coming together to argue about parameters of a knowledge product in the way that you sometimes see in K-12 studies, where they look at epistemology at the level of a student group or a classroom. Here, although there are brief periods of folks kind of interacting in think, pair, share type settings, for the most part, they're doing these things as individuals when they're engaging with assessments. That is a wholly individualistic task, which I acknowledge is probably pretty problematic. And so we don't have the ability analytically to look at some of those kind of communally negotiated aims, reliable processes, and the like that you maybe are referring to from the K-12 setting. Melanie has another thought.
Melanie, take it away.
Okay, so I'm also going to end on a more upbeat note, which is, and I'm going to actually talk about Liz Day's work in green chemistry, in which she has been, and we have been developing case studies, okay, in organic chemistry, which have different outcomes. So students have to choose, and we are trying to get them to use engineering practices rather than science practices to think about the problem, evaluating solutions, and deciding on which, making an argument about which the best solution is. But these are terrifically difficult ideas. They take a huge amount of time. And I want to go back to this idea that, if we had students every day for an hour, every day, instead of every week for an hour, I think we could do terrific things. So yeah, we do have to push back, but somebody's got to pay for it. There are ways that we can we can really improve. Well, in my opinion, how we educate students, but as long as we're relying on this model where there's 400 students in a course, we are constrained. So we have to think really carefully about how we can go about doing that. But it is possible. So I want to end on a good note too. So there you go.
Thank you.
All right, I'm going to call it. Thank you both for sharing your perspective and for initiating this conversation. Thank you to all the folks that asked questions and got us to think a little bit more about this. And we will post the recording for this on the website where we house the rest of the videos.
Thank you all. We look forward to further conversation.
Yeah, it'll be great. We got to fix the system, right? Let's just. No problem. Hopefully that was the right